Hi, good afternoon, everyone. I think now we can start the session for the segment routing for IPv6. Even before this, in the morning, there was session about the IPv6 and 5G and how we can build the synergies about using IPv6. But this session is we are just focusing about the segment routing using IPv6 data plane. So before we start the session, I will just go through the agenda and few of the introduction slides. Uh, so this session is about the segment routing using IPv6 data plane. Uh, I've already prepared a course material page for this course, and this page is available on the academy.apnic.net. There, if you will go to the current events, so you will find the session about the segment routing using IPv6 there. So all the slides, the material is available there, so you do not need to record anything on your behalf, or you do not worry about the slides. So slides are available in the PDF format on the academy.apnic.net /en/events. Uh, just a few words about the APNIC Academy. So actually APNIC is a regional internet registry. You may be already aware of it. So we have a Academy platform which actually offer the free online courses and free labs as well. So anybody who have an email address, he can actually go to this platform and do the online labs as well. Just to save the time, I will be skipping few of the slides. Uh, just another thing of interest, APNIC Foundation, which is a sister concern for APNIC, it actually provides the grants for the development of internet in the Asia Pacific region. So ASIF Asia actually request for the application from the community within the Asia Pacific region, and these grants could be used to build infrastructure and provide services to the community, like maybe you have some project where you need some funding, so you can apply, and they will check your like application, and if they think like this qualifies, then you can get the funding, and you can complete your project as well. So this year the application are going to close by 4th of April. So if you can apply before the 4th of April, your application would be considered there. We are available on the social media platform, so if you want to get in touch, please feel free to get in touch with APNIC. Let's now start the actual presentation about the segment routing. So I just explained earlier, if you need to download the slide, so this is the actually the Academy page. So if you go to the APNIC academy.apnic.net, there you will see this events. So click on the upcoming events, and you will be able to find the second link there, APAN59 segment routing over IPv6 data plane. So if you click on this page, it will open up the page for this session, and go to the course material. Click on the course material. There you will find the day 1 session 1, and next to the presentation tab you will see the PDF. If you open it a new window, you will see the PDF. So all the slides are available here, what I'm going to present in these sessions. Okay, so let's start the presentation, because we have just 2 sessions. So in this session, first session, I will be presenting the only the theoretical part of the segment routing. And in the second session, after the break, we will have the lab. So then you will have the chance to practice or to implement the same thing using the APNIC Academy. So we have the lab available on Juniper and Cisco as well. So any of the platform you want, you can use that. So let's first go through the presentation. So as the topic is about the segment routing IPv6, so I will be touching these of the items when I will be going through the presentation. So in a brief, what is the segment routing in just a few words? So in case of segment routing, the source actually it determines the path a packet should take. It's not the normal. In case of normal routing, what we are doing, that's the destination based routing. In that case, when a packet goes to a device do the longest match, and it actually finds the best part and forward the packet. But in case of segment routing, we are saying like the source who is sending the packet, he should actually dictate what path the packet should take while it reaches to the destination. So how it is done? This is done by encoding the path information within the packet in a sequence of segments. So the instruction is available as a additional information along the original packet when we are sending the packet, and this includes the list of different segments or list of different nodes that needs to be traversed before the packet reaches to the actual destination. So this help us to actually improve our network in terms of reducing the network state, and also it help us to centralize the path computation, which actually if we look into the traditional routing, that's done in a decentralized manner, and every device is actually looking up at the packet and then forwarding to the one hop closer to the destination. So in case of segment routing, IPv6 data plane, remember there are two ways we can do the segment routing. One is MPLS, another is using the IPv6 as a data plane. So we will be just focusing on IPv6 due to the shortage of the time we have. So in case of IPv6, the IPv6 is used as a data plane for the segment routing, and it is in short referred as SRv6. And actually, in order to enable this, we use the routing header, and within the routing header we have the type for segment routing header, which we use to achieve this. So here the segments, they are encoded as a IPv6 addresses when the packet is sent from the source to the destination. So first node, it will actually build the segment routing header, and it will attach that segment routing header when it is sending the packet towards the destination. So in short, this segment routing header SRv6, it's called also a SRv6 segment, and its value is equal to the IPv6 address, which is 128-bit value. And the segments, they are present in an ordered list. So it's not like it's randomly generated. We have a certain ordered list of segment which needs to be attached. So the execution of the when the nodes they are executing in same ordered manner as well. So active segment is put in the destination address, and when the packet is traveling along the path, the destination keep on changing because the next segment is put as a active destination. So then the device is able to forward the packet. So if we just look at the IPv6 header, maybe you are already aware like how the IPv6 header look like. We have like version, traffic class, flow label, payload length, and other field source, destination, and option. But I will focus on the next header here. So you can see here we have the next header. So this actually next header help us to attach the segment routing header with the basic IPv6 header. So in next header, we actually put the information about the upper layer protocol. So here the upper layer protocol would be segment routing header. So that's why we have to mention in the next header what is the upper layer protocol, and this is how we do the chaining or stitching from the basic header to the segment routing header. So in extension header or the next protocol header, we can also mention other protocols information, but in this case, we will be focusing on the segment routing header only. So this is the segment routing header, the routing header, and within that we have the segment routing header, which is type 4. So this type 4 is mentioned in the routing type within the routing header as well. So remember, initially the routing header type 0, it was deprecated because of the security concern, and but the segment routing actually uses the subtype 4. So this is just to avoid the confusion, like maybe someone think, okay, why it's depreciated, why still is in use? But no, the type 0 is depreciated, but type 4 we can use, and we use this for the segment routing. So if we look more in detail into the segment routing header, we can see what are the different fields we have in this case. We have the next header field, and next header field actually mention the upper layer header we have, which is the segment routing header. Within the segment routing header, we have the like last entry, list of segment, and the optional TLVs. So list of entry actually tell us what is the next segment which is going to be executed, and the list itself gives us the list of the total IPv6 addresses we have there in the segment routing header. They will be like starting from like segment list 0, 1, 2, 3 and goes up to n as well. So if we talk about the operations within the segment routing, they are similar to like MPLS. Like in case of MPLS, we have the push, we have pop and continue. Similar here, we have the push operation. So when first time the packet comes in, the segment routing header is attached by the first node. So the first node, it will attach the segment routing header, that is called the push operation. And after that, the next node, depending on that node supports the segment routing or it is just an IPv6 node. If it's just an IPv6 node, in that case, it will do the continue operation. But if it is supports the segment routing, then it will actually do the next operation. In case of next operation, it actually checks how many segments they are left. So based on that, it decrement the segment left by 1 and then removes the next segment into destination address field and then forward the packet. So this is gives us like how the segment routing header look like. So this is a simplified form. Like we have the basic header, which is the IPv6 header. We have source and destination, and after that we can see here SRh. So this SRh is the segment routing header. So within this SRh, we have different fields. Like we have the list of segments, which are it's specifying what are the different nodes that it's going to travel, and then we have the payload. Other than that, like source and destination, that would be available as they are in the IPv6 in IPv6 packet. So let's see how the operation, what are the different types of nodes we have. So in case of segment routing header, we have the source node. So source node is the node which is the first node when a packet comes into the segment routing domain. So it actually attach or is push the segment routing header. So it is the first node from where the SRv6 is going to start. So it will push the segment routing header on top of the payload or the IPv6 packet it has received. So once the payload comes in, you can see it is the payload, then it is going to attach the IPv6 header and then the segment routing header. So there we have the source address, which is same as the source node. Destination address, this will be the next segment, which is in the first segment, which is in the list of segments. So R3 is the first segment coming, so it will put R3 into the destination address field, and then the segment list how many segments we have, it will be equal to segment list n minus 1. So here we have two segments. So segment list n minus 1, 2 minus 1, it will give us the value of 1. So next node we have, that is a transit node. So in this case, the transit node is the node which actually uh, uh, it actually could be the two cases. Either it does not support the segment routing, or it's not present in the list of segments. So here we can see the list of segment only have R3 and R5, and R2 is not mentioned there. So in that case, R2, it is actually acting as a transit node. So it will not do any operation on the segment routing header. When it receives the IPv6 packet, it will just forward it as like in case of normal routing it needs to be done. So this could be your legacy device which maybe does not support the segment routing. So you can still use some old devices which support the IPv6, and you are able to actually enable the segment routing even by having them in your network. So in this case, it is actually just need to do the continue operation, receive the packet and forward it to the next node. So when the next node actually receives the packet, so it will check like so this is the segment endpoint node. This could be the like node in the middle, or it could be the ultimate node as well. The segment endpoint node would be a node which actually see its destination address same as its own address. So here, when the packets comes in, we can see the destination address here is same as R3 address. So when it sees that destination address is same as its own address, then actually it needs to do to process the segment routing header. In order to process the segment routing header, it needs to decrement the segment left field by 1. So it's already 1. When it's decrement 1 minus 1, it becomes 0. So then it goes to the segment list and see what is the segment specified at the 0 position. So at the 0 position, we have R5. So in order to forward the packet, it moves the R5 address into the destination field, and then it forward the packet to the next node, because it will look up how it can reach to R5, and then it will forward the packet to the next node. So now when R5 will receive, you maybe have noticed the destination address, it has changed to R5. So this is how the difference of transit node and segment endpoint. Segment endpoint node need to process the packet, the SRH, whereas the transit node does not need to process the SRH. So now when R4 will receive the packet, the destination address is R5 address, and the segment left is equal to 0, because the previously R3 has processed the SRH and segment left field has been reduced to 0. In this case, when R4 receives the packet, so because the destination address is R5 address and this is R4, so destination address is not matching the local node address. So now it does not need to process the segment routing header or the SRH. It will just do the normal routing. It will see how it can reach to R5, and it will just forward the packet towards R5. So in this case, you can notice like destination address is same as R5, and there is no change in the SRH, and the packet reaches to the R5, which is our ultimate segment endpoint. So when the packet reaches to the ultimate segment endpoint, how it can know like what are the different operations it's need to do. So first thing is it will check the destination address, which is same as the local address. Okay, so then it need to process the SRH, but when it look the segment left field, so like segment left field are already 0. So that means there is no more segment to process further. So in this case, it actually remove the SRH and check what is the information in the payload and forward the packet based on the payload information to us. Maybe it's a host attached there, or within the payload it has the information to look up a certain table or whatever the information is available. So now it will just scrap the SRH, it will remove SRH as there is no other segment left after this, and the destination address is same as the local node. So it will just forward the payload information. So this is how, in case of segment routing, we have just seen when the packets comes in on R1. So R1 will create the segment routing header. It will forward. What it will do? It will create the list of segments that it needs to be travel. Then the list of segment will give you the number of segments. So you have n-1, that is your number of segment. The segment list, what will be the value, and list of segment is the actual nodes that needs to be traveled, and it will put the first segment in the destination address, and then the other nodes will keep on processing based on the header we have. Any questions? Maybe it's if you are first time seeing it, it takes a bit to digest it. That's why I just want to give you a couple of seconds. So in this case, just let me summarize it again. So R1 is our first node, which actually when we receive the IPv6 packet, it creates the segment routing header. So in order to create the segment routing header, it needs to know how many different segments that it needs to travel or it needs to put in the list. Then it gives you the length of the list as well. So length of list is n-1. So total number of segments minus 1 is the length of list, and then it puts the first segment into the destination address and forward the packet. Now depending on the upcoming nodes, they could be supporting the SRH, or they could be actually just the plain IPv6 nodes. So in that case, they will check the destination address. If destination address is same as their address, then they can actually process the SRH. If the destination address is not same as the local address, then they just forward the packet without doing anything. So this is the basic principle how the nodes process the packet in case of segment routing. So just to revise what are different operations each node does. So first node, the initial node, it will do the push operation. So in case of push operation, it needs to attach the segment routing header. And the other nodes, which is the R2. So R2 actually does not find its own IP address within the segment list. So it just need to continue the forwarding the packet. But the next node, which is the R3, is actually finds its own address in the destination address. That's mean it need to process the segment routing header. So it do the next operation. R4 again, it is not present in the list of segments, so it do the continue operation. And the last device, it actually needs to pop the SRH, and there are two different flavors. We will talk later on about them, USP or UST, which is actually de-encapsulation, and popping of the SR segment routing header. So then it just forward the packet based on the what kind of instruction has been sent from the source node. Based on that, the destination node will perform the function when it's forwarding the packet. So there are different flavors. As we see, like when the packet reaches to the destination, then destination need to know what it needs to do with this packet. So there are different ways, like we can tell the destination are different behaviors which could be implemented on the destination node. Then it can act accordingly. So like one of them is the pluntimate segment popping. So the node 1 before the ultimate segment, it can pop the segment routing header and just forward the plain payload towards the endpoint node. The other one is the USP, the ultimate segment popping. Actually, in this case, the last node, it will pop the segment routing header and forward the just the payload to the server there, or maybe to an application attached there. The third one is the ultimate segment de-encapsulation. So in that case, this could be a case for layer 3 VPN or encapsulation service, where the endpoint node actually, when it receives the packet, so it de-encapsulate the segment routing header and see what is the information in the upper layer. So maybe there is further information, forward the packet to a VPN or to a layer 3 or layer 2 service, or maybe to a cross connect as well. So this behavior is actually implemented when we configure a node. When we configure the node, we actually enable what kind of behavior we want to enable on the node. We will see in the lab when we will go to the lab how to implement this as well. So it is actually the source node who actually decides what kind of behavior it wants the ultimate node to implement. So it signals and it sends that information when it is sending the list of segments. So here you can see we have like just written in a plain form, like we have a like address A and n.usp. So when it will create the list of segment, so it will send this information the first node to R5. Like R1 will send to R5, I need n.usp or n.usd to be implemented or to be processed for this packet. So how the source node process the packet? So in that case, actually source node, when it receives the packet, so there could be maybe a policy or without a policy. So in that case, it actually needs to create the list of segment, and then SRH could be required or could not be required. So remember, in some cases, we maybe do not need the segment routing header need to be attached, because we just want to make sure, okay, if the packet reach to the end node, so we can just specify that end node in the destination address. So if I go back to the example, so here, if I do not need the segment routing header, this whole header, I can just put here R5 address instead of R3. If I put R5, the packet will still go to R5. So in that case, without having the segment routing header, even I can achieve the same thing, because in this case, the next device, when it reaches here, it will just look R5 and it will forward the packet to R3. R3 will look up the destination, it will see R5, it will forward to R4. R4 will see, it will forward to R5, and it reaches to R5, then it will just see what is in the payload and it will forward. So there could be this, we can say this is like the routing based on the best path. So we have still the segment routing using, but without need of having the SRH, because there we are not concerned about the middle node, we are just concerned about the end node. So we just specify the ultimate destination and then you finally reach there. So as we saw earlier, the transit node, it actually does not need to do anything with the inspection of the routing header. Transit node, if it sees that the local address and the destination address is not the same, then it actually just need to forward the packet. The segment endpoint node, as we saw earlier, if it sees like the destination address is same as the address, its local address, and if the segment left is equal to 0, then it needs to process the next header, which is the upper layer header. Otherwise, it decrement the segment left by 1 and set the destination address equal to segment list. What is the like maybe if the segment list is showing like position 1 or 2 or 3, so it will just move that address into destination address field. reduce HRS, thus which I explained earlier, like without attaching the list of segment, you can send the packet to ultimate destination, and there is no requirement in this case to attach the SRH. So this actually help us to, in this case, we are just specifying, okay, I just need to go to R5. So I put the destination address as R3. So it ultimately go to R3. R3, when it sees the destination address as R3 and local address is same, it will just process the SRH, reduce it by 1. So it becomes 0. At 0 position, it is R5. So it moves R5 to destination address. So this is the reduce SRH, like when you do not need to create or give complete list of segment. So when we like any as in case of any other protocol, we also have the concern of security. So when we are enabling segment routing, so we need to protect our segment routing domain from outside and from inside as well. So that means we need to drop any packet which is entering into our segment routing domain, and the destination is the our own segment routing domain. And if any packet is generated from within our segment routing domain and the destination is outside our domain, we also need to drop that. So what does that mean? Let me go back diagram. So if does mean if I'm receiving a packet here and this packet should be without SRH, because this is starting off the segment routing domain and this is like the whole segment routing domain. So that means any packet from outside the domain, it should not enter with the SRH, because this SRH will be generated when packet is received on R1. R1 will not receive any packet with segment routing. So it means like when you are receiving from outside, you just receive the plain payload or IPv6 packet. And second thing, when any node is generating attaching SRH, the destination here, within the destination, you should not have a destination beyond R5 or beyond R3. That means it's going to go beyond your domain or beyond your network. So we should not allow this thing to happen. So when we are enabling segment routing, so we need to think about like we configure our devices. So if they see any packet coming outside our domain with the segment routing SRH information, we need to drop it, and any packet which is generated from within our domain and destination is outside our domain, we also need to drop that packet. So what are the different use cases for the segment routing we have where we can use it? Because we are thinking, okay, we can do this, but at the end there should be some implementation or use case for this. As if there is no use case, then there is no need to to be worried about it. So the first thing is before we go to the use case is just I want to touch about the addressing plan. So as we are saying, this is the this needs the support for IPv6. So we need to have within our addressing, we need to have an addressing plan which actually support the segment routing implementation. So like you are an ISP or you are an enterprise and you have received a /32 address block from your regional internet registry like APNIC, then actually you need to come up with the plan. What is the portion you will assign to each of your node within the segment routing, and what are the different functions that you need to implement? Because within the segment routing, without implementation of function, there is no actually benefit of having this technology. So first we have a /32. Out of this, we can decide, okay, we will use a /48 for the segment routing domain. And within this /48, we can decide there could be a locator. Actually, this is our SRv6 ID. But within SRv6 ID, this is a 128-bit address. We have locator, function, and arguments. It's just like you have in some programming language, you have some part which is a function and then do supply some argument. But it's not that complex. Don't be afraid of the programming here. So first we decided a 48, then out of this 48 we decided, okay, we will have a locator block which is /64. So out after 48 we have 16 bits. So first we have 4 bit, and then we have which is our function bits, sorry, flex algorithm, and then we have 12 bits for the router number. That's mean we can use 12 bits to generate different addresses. So we have enough addresses to assign to different nodes as well. So based on 12 bits, you can calculate how many addresses you can have, 2 raised to power 12. So that will give you how many nodes it can support. If you think you have more nodes, then maybe instead of assigning a /48, you can assign a /40. And then you can have like more bits for the number of nodes in your address space. So in this example, we are seeing like we have a 32 assigned from the regional interregistry. Out of that 32, we have taken a /48, and out of that /48, we have assigned a /64 for one router. Okay, so that's mean all the different functions or behavior we need to implement on this node, they will use this /64 address. And out of this, like this is our /64 part, and then we are seeing we have 16 bit for the function. So we have after this we will specify and use next 16 bit for the function. If I need to implement one function, I will use one address, then for the second one I will use the next address, and this is how I will keep on using different addresses out of this 64 as well. So let's see a basic use case in this case. So this is our topology we have. This is our segment routing domain, and we have like R1, R2, R3, R4, R5, and R6. These are P routers, and we have two P router as well, like P1 and P2. So remember, in case of MPLS, you have PE routers, which actually you use to terminate the customer devices. Like the CE devices you connect on the PE, and the other devices, these actually are the P devices which just actually forward the labels. So then we need to decide like different segment IDs we will assign. So we have decided like a /128 for each of the routers. We have the loopback address, and we have two hosts as well. So remember, these two hosts, these are part of the segment routing domain. They are inside the domain, not outside the domain. So that means these are even the host, these H1 and H2, but they actually support the segment routing. So just which it's just illustrating the same thing which I explained earlier, the segment routing edge router, which are used to provide the connectivity to CE routers. And these are our segment routing domain router, which are P routers. So in terms of securing this domain, we actually need to secure it from, this is our boundary where we need to secure it. So if CE router, it will send any packet with the SRH, then we need to drop it, because from here we are only expecting a plain IPv6 packet or IPv4 packet. So that means we need to drop it at our PE router if we receive a SRH packet, and if the destination address is our own domain, we need to drop it. So we need to do this on the all different sides or on the edges of our network. But if we generate any SRH and the destination address it's actually not within our domain, then we also need to drop the packet. Because if the destination is beyond our domain, then we also need to drop it. So how the host to host routing happens in case of segment routing? So in this case, actually our objective is to deliver traffic between host 1 and host 2, and the traffic should go via the R5. So how the segment routing header, it would be built in this case. So this is our desired part that we want to take between H1 and H2. So let's see what are the different things that we need to do. So in this case, the H1, it will build an IPv6 packet with the segment routing, and the source will be H1, destination will be R5, not H2, because we need to build the list of segment. And once we build the list of segment, we are saying like traffic when go from H1, it should pass from R5, then go to H2. So the list of segment is first segment, then the next segment. So the first segment needs to be in the destination address as well. And then we calculate the segment left field. So segment left is equal to number of segment minus 1. So we have two segments, and minus 1, it will give us value equal to 1. So once the segment routing header has been built by H1, because it supports the segment routing in this case, even it's a host, but it supports. So remember, it's not only the routers who actually can support the segment routing, even the Linux host, they can also support the segment routing. So H1 has built the segment routing header. So this is the header it has built, and the destination address is R5. So the packet goes to R1, and then after that, R1, it will look up, destination address is R5, so it will forward the packet to R5. R1 will not process the segment routing header because destination address is different than its local address. So in this case, the packet will go to R5, but now the destination address, it's same as the R5 address. So it needs to process the segment routing header. So it will decrement the segment left SL by 1. So SL will become from 0 minus 1, it will become 0. It will go to the 0 position. At 0 position, it has H2. So it will move H2 into the destination address field. And then it will actually look up how it can reach to H2. And then R5, it will, since it based on the metric we have specified here, it will forward the packet to R3. So these are the different operations that I just explained. It will do, the R5 will do, and it will forward the packet after doing these operations towards R3. So now the destination address, it is H2 when the packet reaches to R3. So when packet reaches to R3, R3 will does the lookup, because the local address is not same as the R3 address. It just needs to forward the packet towards H2. And when H2 receives the packet, the destination address is same as its own address, and the segment left field is 0. So that means there is no more segment left which it needs to be processed. So it will just scrap the SRh and process the payload in this case it has. So this we saw the previous case, it was using the traffic engineering. Like we have specified the path here that we are going to take. Like we have specified path R5 then R2. But what if we want to do the same routing without specifying the path, and we just need to do the shortest path? So in that case, we do not need to specify the list of segment, only the source and destination we need to specify. So in this case, our objective is to deliver traffic between H1 and H2 via the shortest path. So what is the shortest path in this case? So let's see, this is our shortest path, because based on metric, you can see here we have the default metric, which is 10, and on other interfaces we have 20 metrics. So it will go over the shortest path and it will reach uh, using R1, R2 and R3. So if we need to use the shortest path, so how we will build the SRH? So in this case, H1 build an IPv6 packet without the segment routing header. So we do not need to attach the SRH, because if we just specify the destination address, it will go up to the H2. Okay, so in this case, the source is H1, destination is H2. When the packet reaches to R1, so it will do the normal processing, and it will look up the destination address and forward to R2, because there is no even the local router, it's not seeing its own destination address and there is no SRH. So it just need to do the forwarding based on the shortest path. And in this case, again R2, it will check the destination address, which is H2. It will forward the traffic to R3, and R3 will receive and it will forward to H2 as well. So this is similar like what is the nowadays we are doing the routing as well. Once it reaches to H2, H2 sees its own address as the destination address. So then it actually just need to process the payload, because there is no SRH. So it will just scrap the basic header and process the what is available information in the payload. So in this case, what we have observed is, like when a segment routing header is used, in this case we have not used it because we are using the shortest path, and in that case actually the behavior is similar to the traditional or standard IPv6 routing. And the other thing we need to be aware is, like the destination address should be the same address as the destination you want to reach, and it has not changed throughout the traveling of the packet. The H2 was the destination address and it remained the same as well. So when you are processing the SRH, then the destination address keep on changing, but in case of shortest path, the destination address does not change. The next we have the VPN use case. Again, in this case, the similar addressing plan we have, which we saw earlier. So in case of, we have the similar topology just for the ease of understanding. So again, in this case, we want to deliver the VPN traffic using the traffic engineering. So we want to deliver the VPN traffic over a certain path instead of the best path. And our VPN customer is C1 and CE2. So let's see how we go through. So this is our objective: deliver traffic between C1 and C2 via R1, R2, and R6. So this is our path. So it's a kind of a zigzag path we have. So how, in this case, what are the different steps that we need to take? So first we need to see how the C1 and C2, they are able to discover each other. So the C1, it will send a packet to P1. So C1, it sends a packet towards P1. So P1 has to send the packet towards PE2. So once it reaches to PE2, then it will go towards CE2. So this is our, again, the objective. The packet will come in, and it's a data packet in this case. So PE1, in this case, it actually needs to build the segment routing header based on our path. So our path is R4, R2, R6. So that means we have 3 nodes. R4 is the first one, R2 next, and R6 is the third one, and ultimate is the PE2. So it will build the list of segment. Here you can see the list of segment it has. And how many nodes we have? We have 1, 2, 3, 4. So the segment left is equal to number of nodes minus 1, So it will be 3 because here we have 4. So it will build the segment routing header, and what is our first node that needs to be put in the destination address? It is R4. So R4 will be put into the destination address field. So then it will look up at the R4 and forward the packet towards R4. So now the packet, when it reaches to R4, so it sees the destination address is R4 and segment left is equal to 3. So as the destination address, so this address and this address is same, so it needs to process the packet. So in order to process the packet, what it does, it actually reduces the segment left field by 1. So segment left is equal to, it's equal to 3. It's already 3. So from 3 it will minus 1, and now it will become 2. So that means it needs to go to the position number 2. So position number 2, it is saying this position. So this is 0, 1, 2, 3. So remember, it's starting from 0, not from 1. So it will go to the position number 2, which is, in this case we have R2. So it will put the R2 into the destination address field and forward the packet towards R2. So it will forward the packet towards R2. R2 will see the local address is same at its own address. Okay, so it will decrement the segment left field by 1. So now instead of 2, it will become 1. So now it will go to the position number 1, and at position number 1, it sees there is the address for R6. So it will put the address of R6 in the destination address, and then it forward the packet based on the next lookup, and the packet reaches to the P2. So packet reaches the P2. Now when P2 receives the packet, segment left field is equal to 0, and the local address is same as the destination address. So that means it is the ultimate segment endpoint node. So when the packet reaches to ultimate segment endpoint node, it needs to do not need to process the SRH. It will just scrap the SRH, and it needs to process the packet based on the payload or the next header field it has.
So before we define the path, do we need to tell the matrix also? How much segment will be there?
No, the metric we have put there to help us for the shortest path for the IGP. Because if we do not specify, if you have specified the list of segment, it will ignore the metric. So the metric will come into play when you have not specified any list and the routing is based on the shortest path. It just like this, we want to go from this room to the downstairs, and there are 2 lifts. Okay, we have specified the priority for list 1 is 10 and the other lift has 20. But if I say someone, okay, you need to go to the lift A or B, so regardless of the priority, he will go to that lift. He will ignore the priority or the other information. So the segment, when we provide the list of segment, the metric will not be considered. So in this case, even you are seeing it is going from R2 to R6 and P2. So metric here is like 20 and 10, 30. Here is only 20 if we take this path. So, but it is not taking the path from R3 to R5. The next example we have based on the shortest path. So in this case, our objective was actually to deliver traffic via R4, R2, R3. So this was our objective, go like this. So that's why we have to give the list of segment R4, R2, R6 and PE2. Only then we can achieve it. If we want to send someone from like Yokohama to Tokyo, so he will just take whatever is the shortest path. But if we ask him, no, you need to go to another city, maybe Kyoto, So then he will go first to Kyoto and then to Tokyo. So that is giving the information like list of segment. Okay, so first the ultimate, when the packet reaches to the P2, it will forward towards the payload towards CE2. So this is how we will achieve the connectivity, or able to deliver the traffic from CE1 to CE2. So let's see what's the next. That is the shortest path. I'm just going like in a like maybe not slow, because I have like a lot of content to cover, and we have just like 1 hour 30 minutes. So if you see like I'm going too fast, just let me know. So in this case, we have VPN, same VPN traffic, but we want to do the shortest path. So this time it will be based on the metric, not based on the list of the segments.
Another question, why we are considering this one is a VPN? Because it is point to point, right?
Yeah, because we are providing
Uh, Hello, this is Shayok. I have a question that why we are considering this one as a VPN, because this one is point-to-point communication.
Okay, so let me clarify. This is our segment routing domain. Okay, so any traffic which would be beyond this domain, this red line, that's outside the domain. Okay, so in one terminology, we can say, okay, this is the connectivity between 2 points, but this is not part of this domain, and we have to provide this connectivity as a VPN. Otherwise, this traffic will become part of our own network. So these two nodes, the CE1 and CE2, this is not the node belonging to the same network. Remember, maybe I can easily say, okay, this is an ISP, but within educational network, you can maybe have few departments which are present in different cities, and you do not want to interfere, or do not want to merge the traffic into your network, and just want to give them a path over your network. So this is kind of an overlay service. So this is C1 and C2, they are using an overlay service, and the network which we have is the underlay network. Okay, so our objective in this case is to deliver traffic between C1 and C2 using the shortest path. So based on the metric, this is the shortest path we have, because the other links you can see we have, it could be like, maybe you can think of this link as well, shortest path, but here we have specified metric 100 just to make it not the shortest path. Because here if you calculate 10, 100, 110, and again 10, 120, and then 130. But on, if we go to the this link, it's 10, 20, 30, 40. So that's why the upper link, it's become the shortest path based on the metric we have specified. So we have checked the flow. So what will happen in this case when the packets comes in? C1 sends the packet to P1, and P1 need to send towards the PE2, which is the so it can reach to CE2, which is the ultimate destination in this case. So how the SRH, how the segment routing header, it will be built in this case. So let's see when the packet will come in. So we have the plain IPv6 packet, and then the payload. And in this case, we do not need to attach the segment routing header, because we do not have any list of segments. We just want to do routing based on the shortest path first. So that's why we are putting the destination as a P2. So when P1 it is source and destination is P2, it will forward the packet towards R1, because first P1 will look up the packet and it will forward. So it calculates the whole like path, not from here to here. It sees, okay, this is 140 and this is only 40. So that's mean it needs to use this path. So it sends the traffic towards R1. So now R1 will receive the packet as there is no SRH attached and the destination node is the PE2. So every node just need to forward the packet towards PE2. So it becomes like the traditional or standard IPv6 routing. So every node will keep on forward the packet towards the destination. When PE2 will receive the packet, it sees its own address in the destination address at its own address. So it need to process the payload. So then it will process the payload and send it towards PE2. So in order to do that, it will actually see what is inside the payload. So it will look up, okay, there is a VPN table, a VPN label attached, which will actually help him to identify the local VPN, because there would be maybe another VPN here. We can have maybe another VPN which is like CE3 here. So it need to know either it need to send towards PE2 or towards CE3. So based on the VPN label, it will be able to identify, okay, to where it needs to forward, because earlier it has received the when the routing information before forwarding, it actually learns the control plane information, where it actually learns from where it has received the route. So it has received this information earlier, the CE2. That's why it knows like it's sent towards CE2. So it will send the packet towards PE2. So this is how using traffic engineering and using the shortest path, we can provide the connectivity to a VPN customer, or provide an overlay service to another department using the traffic engineering and using the shortest path as well. So let's see, the next is the SRv6 network programming. So actually the SRv6 network programming, it's actually a mechanism to specify the process that the IPv6 header needs to take when it reaches to the ultimate destination. So in this case, we can specify an instruction which actually represent a function, and in that case, the local node, when it reaches to a certain node, then it, based on the local implementation, it takes up action, or it performs that function capability and process the packet. So if we again look at the segment identifier, which is a SID, we called it, we have locator, then we have a function block, and then we have the arguments. So when we are specifying the segment routing address on a device, so although we have the locator block, so here we have a function block. So using this function block, we can implement different functions. Okay, so it's similar like when a restaurant like receive the order, so it has different menus, like maybe for meat it can have different menus, for vegetarian they have a different menu, for maybe for salad they have different menus. So that's mean this is the functionality that a restaurant has implemented. So now any order, when it reaches to the restaurant, it can process those order. But if a restaurant is not like have implemented, it's just providing one kind of food, then it cannot process the order other than that. So that's mean when we are going to configure our device, we have to enable these functions, because this is not going to be enabled by default. So what we want to achieve, we have to enable on the device. And enabling this is the only way through addressing. Like we have the IPv6 address, using that IPv6 address, we will enable, okay, this address is belongs to this function, this address belongs to this function. Do not be like worried too much, because in the lab, you will be able to configure this and see how we enable these functions as well. But in total, when we are enabling this function, our address should not be greater than 128. It will be less than or equal to 28. So it could be less than, because we can leave the few bits as 0 like we do not fill, and automatically in case of IPv6, when you do not specify any part of an IPv6 address, it is assumes at 000. So within locator block, we have the SRv6 SID block and the node ID. So this node IDs actually help us to specify or identify a single node. Again, in case of like we said earlier, we have in case of SRv6 the SID function, which we actually are implemented on the local node, and when the packet reaches to the node, then they are executed. And we also have the arguments, which could be the additional information that with actually associated with that function as well. Other than that, on an SRv6 endpoint, we can have different kind of behavior, like we saw earlier, PSP, USP, UST. So these actually behavior also help the device to provide the functionality which have been implemented there. So within SRv6, we have two kinds of SIDs when we say segment routing identifiers. One are the routable, the other are the routable. So the routable SIDs are which could be reached or which could be routed within the network, and the non-routable are which cannot be routed, and you need the help of the routable SIDs to actually to reach to non-routable. So we have something which could be traveled, and some addresses or SIDs which we cannot use for the routing. So you use the routing SIDs actually to reach to non-routable, and one of the example is like the SIDs between one link to another link. So actually the device, any device is responsible for its own links. If you say to device like which is beyond that device, like R1, to have take action anything which is connected with R5, so R1 doesn't know what is connected behind R5. So first packet needs to go to R5 and then it needs to go. So like we can say from R1 to go to R5, but we cannot say from R1 go to a certain link of R5. So first you need to reach to R5, and then you can say R5, okay, send traffic on your first link or second link or third link. Okay, so this is the list of different endpoint behaviors and functions we can implement on the segment routing, a segment routing node. So we have the, I have just like given the different colors to different endpoint behavior, like we have end.x or end.t. So these are all the behavior related to a segment routing node itself. But there are other behavior and function which we can implement. These could be related to some of the overlay services we have implemented on the segment routing in case of segment routing, like n.dx6 and n.dx4 and n.dt6. So we have just seen the example of this one and this one when we were providing the VPN service. So that we actually implement using the n.dt or n.dt6. So in case of DT4, we are providing the service to a IPv4 VPN, and in case IPv6, you will use the DT6. And we have some other like behavior and function as well, which are actually used when you enable the policy in case of segment routing as well. So there is a long list of these function, but due to the time I would not be able to like go into detail of each of these function, because then we will be even consuming the whole time, and we will not be able to complete it. So I will request you can maybe read at your own time when you are able to download the slides, and all of these function are have a description as well, And secondly, during the lab, we will be actually implementing these functions, and that will help you to more understand this. So I will leave it to you. So I will just skip this part. So just to revise again the flavors, remember earlier we saw like there are different kinds of flavor we can implement on a segment routing node. So we can have like end.x, end.t. So in case of end, if we are just want the packet to be sent towards the node itself, then we need to specify end behavior. That's mean when the packet reaches a node, he needs to know this is only for himself, not for any service connected beyond it. And if there is a, we want the end node to send the packet towards another link, then we can implement end.x. So then when the packet reaches to the node, it will send the packet to a link, a cross connect which is attached to the node. And we have the third one, end.t. So that's mean when packet reaches to the node, it looks up a certain table and then forward the packet. So it depending on our requirement, what kind of behavior we are expecting from the end node. So these are the three flavors we have in case of endpoint behavior for the SRv6 node. This is again the explanation for those three behavior. So the first is the PSP, which is pluntimate segment popping. So in this case, we want the one node before the ultimate node to pop the segment routing header and forward the plain IPv6 packet with the payload towards the endpoint. So endpoint just need to process the payload. So this is similar to PHP in case of MPLS. So you can maybe refer as a PHP, pluntimate hop popping, in case of MPLS. So similar here is the PSP. Another is so this is again the given the benefit of PSP. So the ultimate node does not need to process like the SRH and then process the payload. So it just need to do one thing instead of doing two things. So next is the illustration for the same. So when the packet reaches to the second last node in the segment list, it does the PHP. So it will, because there is only R5 left, so in this case it will move the R5 here and it will scrap the SRH, because you do not need the SRH any further, because there is no need, no any node left, there is just one node left. So it will forward the packet without the SRH, and then the packet reaches to R5. So R5 in this case just need to process the payload, it does not need to have the SRH. So this is just to be more efficient, or to be like instead of doing two things at one node, we are doing one thing at the endpoint node. The USB is again another endpoint behavior, and in this case, source node actually uses the USB flavor when it wants to tell the ultimate node to actually remove the segment routing header from the IPv6 packet and leave the IPv6 packet intact only. So let's see how how it works actually in this case. The segment routing endpoint node just a minute. So when the segment routing endpoint node receives the packet and the destination address is same as its own address, then it will check either the it's the ultimate node for this segment, and then it will remove the SRH from the packet, and then it needs to process the next header in the packet. The last is the UST. Again is the in this case the ultimate node actually it needs to process the inner packet, but before that it needs to it is encapsulated, so it will de-encapsulate it and it will check the inner packet which could be IPv4 or IPv6 for the overlay services, and it will then forward the packet based on the inner header it has. And this is also used for the TILFA, which is actually the technology or a way we can say to provide the redundancy in case of SRv6. So TILFA actually is the technology independent loop free alternative, which is used to provide the redundancy within 50 millisecond within the SRv6 domain. That's mean if your one of the link goes down, the packet will go to the backup link within 50 millisecond, and it will go to the final convergence path. That's mean it will remain on a path which would be your optimal path, instead of just going on one path and then shifting on another one after few seconds or few milliseconds. It will go on the most optimal path. So that's how the SRv6 provides it using the TILFA. There are other endpoint behavior which are related to the policy in case of segment routing. So I will just skip them and not go into detail. So let's talk about the control plane. So the endpoint in the segment routing, as described earlier, like we need to like discover the seeds in case of segment routing. So how the nodes discover each other, how R1 knows where is R5, R3 or R2, and how they actually share their seeds information or about the locator and function information. So actually we need to leverage the IGP. We need to use the IGP protocol, OSPF or ISIS. So mostly we prefer the ISIS. So in that case, IS actually help us first discover all other nodes within the segment routing domain, and then because it's enable us to share to know the other domains. So based on that, we also able to know what are the different functions which have been enabled on those nodes. So this is how each of the nodes is enabled to know each other. Just like similar, we are in this room or in this session. So if we need to know to each other, we need some sort of language, common language. Then we can speak with each other and know each other capability, or know about each other from where it is, what he is doing, what is his like main area of capability or strength. Or so similar, the routing devices, they actually talk to each other and they collect the information about each other using the IGP protocol, and then they are able to know what is the different function have been implemented on those nodes. So in case of SRv6, we, as the RFC says, the SRv6 network programming refer to the capability of an application to encode any complex program as a set of individual function distributed through the network. Some function related to the underlay SLA, other to the overlay or the tenant, other to the complex application residing within VM and container. That's mean the SRv6 programming is actually referred to as the capability of the devices or nodes which are part of the segment routing domain, and what are the different functions that those have been implemented as a overlay service, or maybe as a some sort of latency service or connectivity that they can provide. So if we look at the like how this whole thing works, so we have the network programming application which actually interacts with the controller of the router, and then the controller actually gather the information using IGP and BGP. In case of IGP, it actually we are able to know the end.x, end.dt, end.dt4, and end.dt. These are the different functions or capability implemented, and BGP actually help us to provide the overlay services using the SRv6 and the IGP as well. So in this case, we need to, as for the other protocol, similar we do here, we use the IGP, actually IGP extension to enable the SRv6 services. And in this case, the SRv6 network programming allows us the flexible way to express the packet forwarding through the specification of different behavior at the segment endpoint or on the transit node. We have also another concept of binding SINT, which is actually related to which is related to this policy in case of segment routing. And in this case, actually header node actually when it receives the packet and it sees a binding SID, that SID actually could be related to a certain policy implemented there. So it will remove the binded SID and attach the policy. And policy attachment mean attaching the list of segment. So when it receives the binding SID, it may be related to one of the policies there. So we have certain IGP extensions which actually help us to discover this behavior and transport the services using the ISIS and the OSPF v3. So what are the different ISIS extension? We have SRv6 locator TLV, we have SRv6 capability TLV. So this actually help us to advertise the locator address. And the second TLV, it actually help the node to describe its capabilities. And then we have the sub TLVs which are helping us to express or to tell like what are the different endpoint behavior have been implemented on this node. And we also are able to cover the SRv6 MSD, which is the maximum segment depth, like how many different segments a node can support. Maybe one node can support only list of six segments, another can support 10 segments. So each node actually tells other nodes what is its capability in case of maximum segment depth. And we need to keep our list of segment equal to the maximum segment depth within our network. So if we have one node which is supporting like 11, another 5, another 4, so our list of segments should be up to 4. Because if it's we are sending a list of segment which is like 5 segments, but it cannot process 5, it can only process 4. So then the packet will not be able to reach to the ultimate segment, it will not be able to read it. So again, the similar, like we said earlier, the capabilities are advertised using the ISIS protocol sub TLVs, and we have ISIS SRv6 capability sub TLV as well. And using these sub TLV, we actually express what are the different supported behavior. In this case, you can see PSP, USD, and USD, and other endpoint behavior. So I will go. Another is like another protocol that we use for the overlay services, which is we use BGP, and in that case, BGP actually help us to provide the overlay services similar like in the concept of MPLS. So in case of MPLS, we use the multi-protocol BGP to actually advertise the different reachability or different VPN services from one PE to another PE. So similar we do here. So when we are using an MPLS data plane, we use the labels, but in this case, we can use the IPv6 addresses instead of labels. And the VPN prefixes within what we are doing earlier, that would remain same. So the ingress P push the service label onto the packet, but in this case, we see ingress P, it will push the list of segments when it comes to SRv6. And what we do in case of MPLS, the egress P is actually use the MPLS service label to find the VRF or the VPN. And similar, it can be done in case of SRv6 as well. So whatever we were doing in case of MPLS, we will do the same, only the outer label, it will not be the MPLS label, it will be the SRv6 label. And the inner MPLS label, that would remain same. So this is how the things are more simplified and easier for us. So let's see how the label are exchanged for a VPN service. So when we have a CE2 attached with PE2, so it receives the routing information from CE2. So it actually provides a VPN label. VPN-X in this case, you can see. So it's the name of the VPN and the label is 124. And this label is advertised to PE2 because we have configured this VPN here and this VPN here. So wherever we have configured this VPN, so the PE router, they will actually advertise this VPN label to all the router. So they know like PE2 is attached with CE2 is attached with PE2. So this is again the RFCs for the MPLS VPN, RFC 4364 and 7432. They actually describe the IP VPN and the MPLS-based Ethernet VPN. So we have layer 3 and layer 2 VPN overlay services. So again, we will use BGP as a control plane and SRv6 as a data plane. So that means we will learn the routing information using the control plane. We will do the forwarding, actual data forwarding based on the SRv6. So this is where we will learn about the routing, and this is we will use for the forwarding. So in this case, the SRv6 seeds that are actually associated with one of the services, it could be like n.dt, which is your VPN v4, and this is your VPN v6 service. And the behavior on the advertising PE router, we will have this implemented, and this is similar to MPLS MPLS service label we have, and we will advertise them using the BGP. So another thing we have in this case is the BGP prefix seed. So this is a new optional transitive BGP attribute, like we have many other BGP attributes in case of BGP protocol. So this actually announces the information regarding a prefix seed. So a BGP prefix seed is a BGP prefix segment, which is a prefix with a BGP prefix SID attribute attached to it. So if any BGP prefix has a BGP prefix attribute attached to it regarding the segment routing, then we call it a BGP prefix segment. And we extend it using the VPN v4 and VPN v6 address family as well. And label is associated with each of NLRI, which is the network layer reachability information in case of BGP update. So we have here also two TLVs, which is label index TLV and originator sRgB block TLV. So the BGP prefix SID, again the BGP SID attribute is further extended to carry the SRv6 SID, and we have the TLVs like SRv6L3 service TLV and SRv6L2 service TLV, which are used to provide layer 2 or layer 3 VPNs. I will just skip this part, and as we are just short time, so I will be trying to cover all and just skipping few of the slides where we have which I think we can skip. So in this case, we can see we have a topology, which is SRv6 based BGP service. And so we have PE node, which actually advertise the, when it receives the information from CE1, the routing information, it will advertise towards PE1. And here you can see the endpoint behavior it will advertise, and the service SID, which is also an IPv6 address. So it will send him, if you want to send any information towards CE1, then use this IPv6 address and mention this endpoint behavior. So this is how the PE1, when it need to send information towards CE2, it will use this IPv6 address and send the traffic towards PE1. So we again have this we already covered, like the shortest path, which is called the best effort, where we actually use the shortest path to deliver the service. And the other one is the traffic engineering, which is like the based on the certain constraint, we actually want to deliver the traffic. So in case of certain constraint, we use the traffic engineering, and this could be the SLA could be based on the, like, maybe you have a requirement for a certain latency or certain bandwidth or avoid certain path. So depending on the requirement, you actually provide this. Again, coming to the use cases like we saw earlier. So we have so in this case, this is representing our SR routers domain, and the routers within this domain, they have seeds and they are advertised using IGP to all the segment routing routers, and the other routers, they also actually they can receive this information and use them for the reachability as well. This similar we discussed earlier. So again, the SRL3 VPN, if we have a VPN customer, so in this case, this VPN, our actually intended to deliver the traffic CE1 to CE2 via the shortest path, and CE1 is attached to P1 and CE2 is attached to P2. We have a VRF, which is VRF10 in this case. So we want to deliver traffic over the shortest path, and so what are the different things that they need to do? So P1 VRF10, it learns the route using the BGP signaling protocol, and then actually it associates this route with the IPv6 address from the it has learned. So CE1, when it sends an IPv4 data packet to P1, and the destination address is the CE2 address. So when it receives the packet, it actually then it needs to send the first it needs to build the SRH and need to send the packet. So it actually put the destination address same as the PE2 address, which actually it has advertised for this VPN. So earlier we saw it has advertised this D4 address using the n.dt function here. So the remaining devices, they will actually keep on looking at the destination address, and the packet will reach to the P1 as we saw earlier, and then P1 actually it needs to look up the upper layer protocol, and then based on that it will be able to identify that it's related to this VPN. So before that, since we have implemented this endpoint behavior here, and based on this endpoint behavior, it is able to know like it belongs to this VRF. So then within the VRF, it will look the IP address, the destination address, and it will forward the packet. So the other use case we have for the segment routing policy. So in this case, instead of going over the shortest path, we want to go over this a specific path, which is going through R4, R5, R3, and then P2. So in this case, we need to attach the list of segment because we are not using the shortest path, we are using a specific path. So when the traffic comes in to P1, then it will actually attach the IPv6 addresses for R4, R5, and R3. So you can see here the first address, this next address, and then the next address. So C1 sends the packet, which is IPv4 packet. So it will just encapsulate it, and it will build the SRH in this case. So when it builds the SRH, it will give the list of segments. So here you can see the actual IPv6 addresses as the list of segments, and then the destination address same as the first address. So the other devices, they will keep on processing, keep on moving the next address in the destination address. So here it will move the next address into the destination address because it has processed the packet, and decrement the segment left field by 1. And ultimately the packet reaches to the PE2. Now PE2 sees the same his own address as the destination address, and segment left field is equal to 0. So then it will need to know what is the, it will just scrap this SRH and match the what is the endpoint behavior it has been implemented there. So endpoint behavior is end.dt. So that's mean look into the specific table and forward the packet. First de-encapsulate, then forward the packet by looking into the table. So PE2, it is the ultimate segment. It will de-encapsulate the IPv6 header, remove the SRH, and then look up in the inner IPv6 destination address in the VRF10, and then send the packet to CE2. Because based on the endpoint behavior, it is able to know which is the VPN it need to forward the packet. Okay, so we are already, I think, over the time. So I would stop here. Even there are few slides we are left. That's also similar to segment routing policy. So I would request if you can come back in the next session. So then I can complete the few of the remaining slide, and we can also do the lab. So you will have the opportunity to do the lab from your own laptop. So I will let you know the address and the link which you need to connect, and then you can do the lab with me as well. So anyone who is online, they can also do the lab. So they can also join us like after the break when we start. Yes, please.
So I have a question that in every destination, the destination address is the same. So and the source addresses are changes for every process.
No, destination address is changing, source address remaining the same.
Source address remaining the same.
Yeah, if I go back, let me just go back here. Few slides. Okay. So see, when the packet from CE1 comes in, no, P1 needs to build the SRH segment routing header. So our objective is traffic will go like this.
Okay.
Okay, if from R5, R3, and P2.
So then how will we get the final destination address?
Okay, so let me. So when we are saying here, the deliver traffic from CE1 to CE2 via the underlay TE1. So this P1 knows where the traffic needs to go because it has learned about this CE2, because the VRF10 is also here and VRF10 is here. So it knows what the destination. The segment routing is only, in this case, the policy is helping him how to reach there. So it knows the ultimate destination, but it also now knows how to reach there. So it need to go to R5, R3, PE2, because PE2 is your destination. So when it will build the list of segment, so it will build the list of segment like this is your PE2, this is R3, and this is R5. Remember, in this case, we have not mentioned the R4, we have mentioned R5. So our first SID is R5. So R5 address is in the destination address. So now the packet will go to R4. R4 will see the destination address is R5 address. It's not its own local address. It's just like I'm giving you some parcel, and I've written the name of the person on the parcel like ABC, and your name is. So when you receive the parcel, you will see, okay, the person who need to receive this parcel, his name is ABC, and my name is not ABC, so I need to send towards ABC. so it will forward to the next. But if it see, okay, the destination address is same as my own address, then it will look into the list of segment, like is there any other hops left which need to be traveled before the packet reaches to the final destination. It will then process those. But if sees, okay, uh, that destination address is ABC, I am also ABC, and there is no more list of segment left, then it needs to unwrap the packet and it will see what is inside.
Another question is, so in the source address, so we need to change the prefix or change the bit to.
No, we are changing the bit here. List segment left field. You can see here, which is 2. So when the packet it has reaches to R5, you can see it is 2. Let me forward it to the next. Okay. When it goes to R5, so now you see the segment left is still 2. Why? Because R2 is not was not in the destination address, so it has just forward the packet. It has not done anything. But in this case, R5 is same as destination, so it will now reduce the segment left field by 1. So when it reduced by 1, so you will see at 1 what we have. This is 0, this is 1. So at 1 we have address of R3. So it will move this address to the destination. So just observe, like at destination what we have now is, so it is 2, and destination we have this 5 here. You can see 5 here. So it will move this 3 when it moves in this direction. Okay, it forward. Now you can see the segment left, the pointer is changing. So this pointer, changing a pointer, is helping us to move the next address to the destination. So now in destination we can see we have 3, which is same as 3 address. So if the local address is same as the destination address, then it will process the segment routing header. Sorry, going over the time, we went a little bit over the time. So we can resume after the break, 15 minutes. And we will do the lab. So in that case, it's preferred you have, if you have a laptop or iPad, that will help you to complete the lab. Otherwise, I can show you the demo, but if you want to do by yourself, then you will need the laptop. Okay, so we can resume the next session. Can we resume? Okay, so in order to do the next session, we have to do the lab in this session. So as I explained earlier, we to complete the lab, the lab is available on the APNIC Academy, and you need to go to the APNIC Academy. So the address is academy.apnic.net. So can you please open it if you want, I can display it. You know. So you need to open this URL academy.apnic.net. If you do not have any account there, so you can quickly create that account. You just need an email address. Just try to create your account, and it will send you a code on your email, and you will be able to log into it. If you need a couple of minutes, just let me know. I can wait. So you need to go to the academy.apnic.net. So once you land on this website, you will see a similar interface. So there you can see, if I click on the courses, I can see course catalog, online courses, virtual lab, past events. So from the past event, from the upcoming event, just click on the upcoming events. And you see here, APAN segment routing over IPv6 data plane. This link, you can click on this link. There are like one ways, like you click on this link and it open the course material page. It will open the course overview page. Then you need to click on the course material. And if you scroll down under the second session, you can see here in the exercise, there is a link SRv6 with Juniper and SRv6 with Cisco. So if you are comfortable with Cisco, you can use the Cisco lab. If you are comfortable with Juniper, you can use the Juniper. So I'm going to use the Juniper for this lab. So you will click on this link and it will open a new window. But you need to first log in. Once you have created the login, then you need to log in. Otherwise, you need to first register there. So you will use your email address to log in. The other way is like when you land on this page, you see this virtual lab. Courses under the virtual lab. You can directly click on the virtual lab. But going from the course material, actually it helps you to quickly directly go to the lab which you are looking for. So if you directly go, then you will see the lab which you need to do. It will be at the top. Otherwise, you have to search this. If you will go to the from the virtual lab link, then you can do Control F and find the lab. So if you go from here, click on virtual lab, it will not bring your lab, attended lab at the top. Then you need to do a Control F and find your required lab. In this case, you can see it is showing me DICP. But when I'm going from the course material, it is showing me SRv6 at the top. So how we launch the lab there? You can see here view instruction and launch lab and monitor. So in your case, you will just see two buttons, which is view instructions and launch the lab. View instruction means you just want to see what is the information within this lab. So if you will click, remember you need to disable the pop-up blocker, otherwise it will not be able to open a new window and you will not see this. So this just give you an overview of the lab, what are the instruction or detail about this lab, if you just want to see the instructions. But if you want to actually do the lab, then you have to click launch the lab, say yes. It will open a new window, and remember, if you have the pop-up blocker enabled, then it will you will see a message here, the pop-up has been blocked. So you need to enable the pop-up, disable the pop-up blocker for academy.apnic.net website. So if you click, it will take almost 2 minutes to launch the lab, and it will open up a new window for the lab. So just wait for the lab to be loaded at the backend. Yes, please. But more or less, or either you do Juniper or Cisco, the instructions are, the steps are same, like the number of tasks are same, and just we are using different devices. Yeah, command, obviously they are different platforms, so the commands will be different. But the task which you need to do are more or less what you want to achieve within lab, that's same. Okay, so once we are into the lab, you can see here the lab has been launched, and now I can see a window where I am seeing the instructions, or you can see here instructions, resources, information. So instruction are the information which is needed to complete the lab, and it's giving me an introduction to the lab, an overview of different overview of the lab, and the task which I need to do, or different tasks I can complete within this lab. So each task is actually helping you to go towards the final achievement or final your goal in the lab. So actually okay, so if you go to the courses on virtual lab, so then you will end up on this page. Okay, so you can do a control F and search SRv6. So it's similar, like I do a control F, search SRv6. So it will show me wherever the SRv6 is available. Okay, so once I have launched the lab, then I will see instruction, resources, and information. Instruction will give us introduction, overview, and the list of tasks that needs to be done within lab. It will give me a topology, the physical topology of the lab. So you can see it's showing me this diagram. Even if I click, it can open a new window which just shows the same diagram. So I can see it is showing me a network which is AS64512. So this is actually our service provider or our main network where we will be enabling SRv6. This could be an enterprise network as well. And we have like 4 hosts attached to it, H1, H2, H5, H6, they are attached with similar router like R1, R2, R5 and R6. And then we have two customer sites which are R101, R201, and then we have two servers S1 and S2 attached. Okay, so we have some information regarding this network. You can read it here as well, which is what I just described. And just about a few of the tips about the lab. You can see these three lines here at the corner. So if you will click here, you see save, end or split window. So that's mean if I want to save the lab at this point, I have done some task, now I want to save the lab because I cannot complete it. So it will save the lab and I can return within 7 days and I can resume from the same step where I have left. Okay. End mean if you click end, you are going to end your lab, you have completed it or you want to cancel it. So if you save your lab, it remains saved for 7 days. So that's mean within 7 days you can return, and after 7 days it will be reset. You can save at a time 2 labs, like, but more than 2 you cannot save, but you can do as many labs as you want, but only you can save just 2 labs. So you see some information, initial configuration. So this is showing us what is the initial configuration on the router, which is already been available, and few of the commands as well. And in this case, the host, which we can see here, H1, H2, H5, they are pre-configured. They are like you do not need to configure any IP on them. Their IP address already has been configured. Only we need to configure the addresses on the routers and the protocol which we need to enable on the router. So let's and similarly you can see here like P1 R1. So this blue is showing me if I will click here. So right now it is showing me H1 here. If I want to do or switch to any other device, I will click here and switch to R1. So it will then show me the CLI for R1. Okay, and if I want to go to like R2, I will click here, press enter, it will show me the R2 device. This is how you can switch from one device to another device. Similarly, if I want to go, you can see here H1, H2, S through. So either if I click here, even still it will change it to H1. If I click H5, it will change to H5, or I can click in the center and then from there, from the drop down menu, I can click on the desired device as well. You can see the username and password information. We have the username APNIC, password is training, TR, A is at the rate, and T is capital. But for the host, we have the username same as APNIC, and the password is training without any like capitals or any special characters. Then we comes down and we have the addressing plan. So here you can see what are the addresses we have used, like the IPv4, IPv6 addresses, SRv6 locator block. As we discussed earlier, like we need the SRv6 locator block, and then out of this block we need to give an address to each of the router which is the participating in the SRv6 domain. We have the VPN site information as well. So site 1, their AS number, IPv4, IPv6, and same information is available in a table here. So you can see here there is a 10/0.0/16. So we have used this network to provide connectivity from router to the host, But within these routers, there is no IPv4 address. You can see only IPv6 address has been mentioned on the different links that we have. But if we go to the customer network, they have the IPv4 network from the host to the router, and from router to the router, because this is a VPN site. This is also a VPN which can have IPv4 and IPv6 addresses. But within our core network, like within our SRv6 network, we have only IPv6 addresses. So why we do not have IPv4 because we want to demonstrate by having only IPv6 addresses, still it can provide the connectivity to IPv4 and IPv6 destination at the same time. Okay, so and you can see some information regarding the pre-configured. They are already configured H1, H2, H5, H6. I will not go into detail. You can see their addresses and gateways as well. So here you see at the bottom next. So this you need to collect when you need to go to the next page. So click next and we will start from the task 1. So in task 1 we have 3 subtasks: configure router IPv4 and IPv6 addresses, verify router point-to-point connectivity, verify LAN connectivity. Okay, so we have the again the diagram which is showing you the information regarding the addresses. Okay, now I need to go to step 1. You can do is just click on this step 1. It will just move down, and here I need to configure the router R1 link addresses. So first let's click on R1. So it will change the console to R1, and now I need to type the username. You can click this C, this T. So if I click this T, the username is pasted on the other side. Then I click on this password, the username is automatically pasted on the other side. Otherwise you can click on this lightning button and type from here the type username or type password as well, if you do not want to type by your hand. So now I have logged into the router. I need to configure. How you configure a Juniper router is like you type the configure command to go through the configuration mode. Then you need to specify the host name, because now you can see APNIC as a host name it's given, but we need to set the host name to PER1. Okay, and then we need to specify the IP addresses on the interface. So first we added the interface, and then we specify like the description, IPv4 address and IPv6 address, because this is our loopback address. We are specifying IPv4 and IPv6, but the other addresses which are from R1 to R2, R3, R4, we are only specifying the IPv6 address. Okay, so let's click on this T and then press enter. So it has configured all these lines. Then you can commit and quit. Before that, if you want to check what is the configuration you have just done, show compare. Okay, it shows all the plus signs. It shows all these lines which actually has been added to the router configuration. So you can see the interface, description, unit 0, family INET, INET 6. So where you have configured IPv4 and IPv6, or where you have just configured an IPv4 address, it will show just. And then commit and quit. Commit, it will apply the configuration and come out of the configuration mode. Okay, after that we need to go to the R2. I will quickly go to the R2. I need to log in, password, and then I need to apply the configuration. So in this case we are applying the whole configuration instead of going step by step, because we know how to configure the router, and commit and quit. After that, go to R3. Do not skip and just keep it doing in a sequence, and give the username, password, configure. Just keep on seeing that configuration is getting applied, and you get the message configuration applied successfully. So you can see here commit complete. That's mean configuration has been applied and it exited the configuration mode, and you can see from the number sign it again changed to the greater than sign. After that we need to go to R4. Okay, and we need to provide the username, provide the password, configure the router. Okay, let's go to R5. Username, password. First time you need to do this, or when the router has timed out. Remember you are applying the configuration on the same router. Otherwise, if you are on R2 and apply the R5 configuration, that will create the issue. If you're doing it first time, just wait a little bit. Okay, it applied the R6 configuration. Now I need to go to the CE1, CR101, login, username, password, apply the configuration. Go to the another router, you need to log in. Okay, once we have done this, then you need to verify the configuration. How we verify configuration? We have given some command here for the router.
If we give command to, suppose I am in R5 router, but giving command to the R6 router.
No, that's incorrect.
Will it work? Because the name.
No, it will accept the commands, but now you have created a conflict because same configuration you have done on R5 and same you have done on R6 as well. So same IP you cannot use twice because similar, like we are here, every one of has unique name, and similar the IP addresses should remain unique as well. If you have the same name, if I'm speaking, both of you will think I'm addressing to you, but actually I want to address one person because this is a Unicast communication. Okay, so in order to see what the configuration is, show router ters match. So we are matching all the GE interfaces and loopback and seeing the matching the IPv6 address. So then it's showing me the IPv6 address. Similarly, I can go to you can see here R1. So I will go to R1, and if I give this command, this in green, it should give me my output should be similar to this blue and black portion of the text. Okay, and this is how you can relate, like local 281/2611 172.20/30 10.2.1.1/24. So this is how you can match, like whatever the configuration you have done, it is right or wrong. If you have done any mistake, you can verify using these commands. And now I need to ping. Just for verification, I will do a ping. So your output will be similar to like this. Similar, I will check the connectivity towards R3, and I can see it's working as well towards R4. So this is how I am verifying from R1. I have configured R1, and from R1 I'm sending packet towards R3, R4 and R2. So this link is okay, this link is okay, and this link is okay. So this is giving me confirmation, like from R1 router I have the connectivity to R3, to R4 and R2 as well. So when you are at the top, even you can click this verify and it will move to that section. Similarly, you can go to the other router and verify, but just to save time, we'll move on. So now I need to check the connectivity towards H1. From R1, there is a host connected on H1. So remember this host is connected with R1. So I need to send packet from R1 towards H1 just to verify that it is connected. Let's go to the LAN part. Okay, so I will ping, and similarly towards IPv6 address. So I can see it's working. Let's go to C router and you can check the connectivity there as well. And similarly to C2, we can check the connectivity. So this is how you are completing configuration, and then you are verifying your configuration at the same time as well. Either you have done it in a right manner or you have done some mistake. So once you have done this part, even you can go to other routers and check the connectivity, but to save time, I have to move it on. So the next task is we need to configure IGP, and in this case, we are going to use ISIS protocol. So if so in this case, what we need to do is we need to ensure that loopback they are reachable, and for this we will use the IGP. Then we need to enable the SRv6 IGP extension to advertise the SRv6 locator block, and after that we need to define the SRv6 locator and enable SRv6 extension. Remember we talked about the enabling the endpoint behavior, so we have to implement here that behavior. And then we need to achieve the end customer connectivity. That's mean H1 to H2 and H5, H6, they need to talk to each other. So we will send traffic from H1 which will reach to H5, and from H2 to H6 using this network. And then the next task is to configure L3 VPN and then traffic engineering. So this is again the showing the routing diagram. We have site 1, site 2, and this is our service provider domain, or the network which is providing the connectivity. You can see here different color has been given to help you to understand different protocols and the domains where they are enabled. Okay, so the next is to configure the ISIS. So even there are other labs where we have given separate ISIS. If you are not familiar with the ISIS, so then I would request you to do an online course on APNIC Academy about the ISIS. I will not be able to explain the ISIS. So we just will follow the configuration here. Okay, and in this case, when you configure the ISIS protocol, you go to the routing option, you need to specify the routing ID, and then on different interfaces you need to enable the ISIS. So we need to give an ISIS address on each of the router. So remember in this case we are using the area 0 for ISIS, and each of the device they has the IOS address, which is the unique address for that device. So there is some explanation here how this address has been calculated. So you can go through this if you need to understand it. Okay, and after this we once we have configured, then we need to go to the other interfaces, disable the level 1, enable level 2, and set topology IPv6 unicast, because we are using the IPv6, and all the interfaces which we want to enable the ISIS we need to list here, and then we need to quit and commit. Let's go to P2, and now similar like other, we will do the all configuration just in one command because we have explained earlier. Okay, once we are on R2, click on this T button. So we have done the configuration. Then on R3, do the configuration for R3. And if like earlier you said you have done the configuration for which was supposed to be on R5, but you have done on R6, so how you can like roll back it? You can go to the configure mode, and here you can roll back, write rollback question mark. So see, it shows me different configuration that I have done on different times. So if I do rollback 0, so it will show me what configuration it going to roll back. So you can check show compare, it's not showing. But if I do rollback 1, so it will show me all the ISIS configuration I have done earlier. So if I do rollback 1, all this configuration will be removed. So you can see minus, so that means these lines will be deleted. So if you do not want, if you have done some configuration and you do not want to apply it, you can do rollback 0. Okay, then again check show compare. So there is like no command. So then I can just exit. Otherwise it will not let me to exit. It will say either apply this configuration or just remove those lines. So I was on R3. So let's see. Let's go to R4. Okay, and Next is R5. Let's go to R6 now. Okay, so this is the end of this task. So we have configured the router R1, R2, R3, R4, R5, and now we need to verify the configuration. So in order to verify, you can see here we have given different commands. You can check show ISIS overview. So it gives you the complete detail of this router, what has been implemented, like the router ID, IPv6 router ID, host name, system ID, and if you have not enabled ISIS, it will also tell you, and you can see here the level 2, level 1 information as well. Then if we click show ISIS interfaces, so it will give us what are the different interfaces on which we have enabled the ISIS, and you can see here level 2 and level 1. Level 1 is disabled, level 2 we have the point to point and the metric as well. And on loopback we do not actually build any adjacency, we just want to advertise. So actually ISIS, what we are doing in case of ISIS, from R1 we have enabled on this interface, and this interface like G00, 002, 001. So that's mean it has built a neighbor relationship from R1 with R3, from R1 with R4, from R1 with R2. So any of those interfaces, it if remains up, that means it can reach to the rest of the network. Similarly, we need to enable from the other side R4, R3, R2, R6, because you build the neighbor relationship from both sides. So you enable one side, then from other side you also need to enable. So how we will verify? Like we have the this has been configured accordingly or not. So you can see I will check show ISIS overview, and then there I have some highlighted here, source packet routing Spring disable. So this is disabled, by default this is disabled, and we need to enable it in the next step. So if I check here, it will show me layer 2. So you can see here source packet routing disabled. It is showing here where my cursor is. You can see here. Similarly, for the show ISIS interfaces, you can do a control C to get back the control. And if you need to check the neighbor relationship, you can give this command show adjacency. That's mean what are your adjacent neighbor. So you can see here state should be up. That's mean you have the neighbor relationship up with the other routers. So your output should be similar what we have displayed here. So up 3 should be up, because this is the relationship with PR3, PR4, PER5. Similarly, you can check the loopback interfaces. Either you are able to see the loopback of other routers. So here I can see R1 loopback, R2, R3, R4, R5. That's mean I'm able to see all of other routers. So remember how many routers we have here. If I'm checking on R6, so I'm able to see R1, R2, then R3 I'm able to see R4, R5, and R6 will not show itself in the routing table because this is ISIS, and it is actually already had its own IP as a connected. So connected has a more preference than the dynamic protocol. That's why it's not showing here, but in the ISIS, because the command is show route table inet 6.0 protocol ISIS, but the local address will be in the routing table, not in the ISIS, because the local has the more preference than the ISIS. So if you see 5 addresses from each router, that's mean your ISIS is configured properly, because each router is able to see each other. Remember, if we have like maybe how many people we have, 5 and 9. If 9 of us can see 8 other people, that means we can see each other in this room. Similarly, in a network, if router are able to see others other than itself in the ISS protocol, that means they are able to discover others. So that's a confirmation, like we have configured it properly. So similarly, you can do the verification on other routers, and this is another command, like if you want to count the lines within the routing protocol, it should count like 6. If you remove this count and just want to match the addresses, you can see here, this is your direct address because I am on R6. Rest have been learned through ISIS protocol. If you want to see how the forwarding will be, you can use this command because it shows you how you are going to reach to other addresses. Like to reach to one, it will use this next stop and this interface. So if I am on R1, let me just explain. Like if I am on R6, the packet will go on this interface. It will reach to R3 and then to R1. The other option is it can go on this path and then go on this path, because we have not enabled multi-path, because you can see UCST, this is a single path. That's why it is showing just one interface here. Otherwise, it can show two interfaces. Okay, so once we have this ISIS has been enabled, then you can verify on other routers, but due to the time I will not verify. When you are doing the lab, please do all the steps, because I can see I have the similar output. Like here I can see 6 lines as well. If I go to R3, I can see 6 line. That's mean they have the same addresses available. Okay, so all of the router, they are showing me same information. So I will just move on to the next part. So this is optional all, like when you have time, then you can do these verifications. So since we will run out of the time, so I will just not do the optional part. So in next step, we need to configure the SRv6, the thing which we have been talking since long. Let's configure it. So there is some explanation again here. So it actually helps you in the lab when you have like doing first time or maybe second time as well. So this will refresh some of your concepts here. So it's better you read these when you are doing the lab. So I will straight away go to the SRv6 configuration summary. So remember we said we need an SRv6 locator block, and from within the locator block we will assign addresses to the devices, and we will assign the address to the functions and use for the arguments as well. So in this case, remember we have locator block, node, locator node block, function block, and arguments. We will use 32 bits for the locator block, 16 bit for the locator node, and for function we will use 16. So if you add 32 plus 16 plus 16, so it's become 48 plus 16, 64. That means for functions we need to use /64. For nodes we need to use /48. So whatever we will assign to node, out of that we will assign to for function as well. So for our address block, I have created this summary here. So we can see if we have the SRv6 SID to decompose or to just bring into different parts. So if this is my /32 address, and this is my node address, this will be my function, this argument, this is unused part. So I have this, our default address in this case is /32. Let me see here, we must have specified. Yeah, so we have this /32 address. So out of this first 32 bits, then next 16 bits I can use for the first node, which will become 1, then 2, 3, 4, 5, 6, and /48. So maybe you have to revise your IPv6 subnetting if you are not familiar how to create /48 out of 32. So as we have created 48, so then we will configure each of the router with their block here. So you can see I have 148. So I will go to R1 here, and here you can see I'm going to the routing option, source packet routing, SRv6 locator, and here I'm specifying SRv6 locator R1. This is the name of the locator, and then /48 address I have specified. So I will go to the router R1. Remember to go to R1, otherwise you will mess up with the configuration. Okay, similarly I go to R2, do the R2 configuration. Now I need to go to R3. So I am adding the locator block on each of the router. Similarly go to R5. Go to R6. So once you have enabled the locator block, then you need to enable ISI's SRv6 extension. Remember we talk about the extension where each router need to advertise its locator block, advertise its capability, and advertise the endpoint behaviors. So let's go to R1 and enable the SRv6 extension. To enable the SRv6 extension, we already have this locator block enabled, defined. So now we need to go to protocol ISIS, source packet routing, SRv6 locator, and just the name of the locator. So when we give the name of the locator, router is able to advertise that locator to other. Similar, I have some information, I'm just already defined, now I'm giving to you, and you will be able to receive that information. Okay, go to R1, I'm already on R1, so I will apply the SRv6, enable the SRv6 extension, go to R2, enable SRv6 extension for R2, go to R3, enable SRv6 extension, go to R4, enable SRv6 extension, R5, enable SRv6 extension, R6. So once you have done this, then you need to verify the locator advertisement. So how you will verify? We'll go again to ISIS overview and find this Spring. Spring is the segment routing, source packet routing. So now if I try to find, you can see source packet routing Spring enabled. So it's showing that I have enabled the source packet routing. So similarly, you can verify on each of the device. If I go to R1, then I can check ISIS database and verify locator advertisement. So you can see here, I see PER1, PER2, PER3, PER4, and PER5, and I am on R6. So from R6, I can see all other routers and their locator block. Similarly, I can check the routing table for SRv6 locator in INET 6.0 for reachability and INET 6.3 for BGP services. So let's check the show route. So when you give the command show route, it gives you the INET 6.0 routing table information. Here you can see all the /48, and they should be in INET 6.3 for the BGP services as well. So in both tables, I can see the addresses. Similarly, you can go to other routers and you will find the same output there as well. So once you have done, sorry. So once you have done this, then you need to you need to define the end SID. So this is the endpoint behavior that we talked earlier. So we need to define the endpoint behavior, because before that, let's try to ping the other router to verify the connectivity. So if I am on R6 and I want to ping the locator block for R1, so you will be able to see I can ping the IP loopback IP address, but if I ping the locator block, which is for SRv6, it is showing me destination unreachable. So that's mean ping to the locator is failing, but ping to the loopback is successful. Because when the packet is going from R1 to from R6 to R1, R1 has not implemented the endpoint behavior, so it doesn't know what to do with the packet and it just drops the packet. So we enable the endpoint behavior. So how we will do it? You can see a command here. Remember, we have already defined this locator block, set protocol source routing locator. Earlier we just defined this part. So now we need to add this keyword end SID and then the IPv6 address, which is we want to bind with the end SID. So this is how you actually implement different endpoint behavior if you need to implement. So earlier maybe it was difficult to understand. Now you can see we just add the end SID and then the IPv6 address. Similarly, you can add other, if you want to enable more than one endpoint, end SID here, you can specify here. But first, the locator need to be defined. That means you can define multiple locator on one router even. So let's do it quickly. Okay, so R1, let's go to R2. R3, okay, I'm not applied on R2. Okay, you can see it just added and SID this, because the previous part we already have done. Like we defined the locator and now we are using the same locator, we are just defining the end SID. And when you are giving the command with plus, it's showing what part you are adding to the previous existing configuration. So just go to the R6 and okay, so once I have defined the end SID on all of the interface, all of the routers, how I can verify it? I can check the ISIS database, use the extensive command, then match SRv6 SID. So you can see here, I can use this command and just match. So instead of having lot of information, I'm just, if I do not specify match, it will give me a lot of information, but I just want to be very specific. So I'm saying match SRv6 and only give those lines. So now you can see it is giving me SRv6 SID for R1, R2, R3, R4, R5, R6. So my all of the routers within my SRv6 domain, their end SIDs, they have been advertised and defined as well. And you can see the flavor. Remember we said we have 3 flavor, PSP, USP, USD, and here it's showing none. That means we have not defined any, we have not enabled any flavor. And now if I try to ping the end node, the end SID for the R1 from R6, so it will reply me. Earlier we were seeing unreachable, but now it will match this output. It is giving me the reply. Similarly, you can ping R2 from R6, but you cannot ping from R6 to R6 because it cannot use its own address to send the packet towards itself as well, because it is unable to process. So if you will ping to other router, they will also be successful. So you have a more like nodes here has been added just to help you to understand these things. And yeah, similar like it's showing if you earlier I explained it. Flavor none. So each of the host name, then it's SRv6 seed, and flavor what has been, if you have enabled any flavor along with the seed. So that's your basic SRv6 configuration. Then you will go to the part 4. So now our network is ready to carry the, like we have enabled the SRv6. But if we want to enable other services, then we need to go to the next step. Now our task is to have connectivity from R1 to R2, R5 and R6. So what we need to do in this case, since this is an overlay service, so we need to use the BGP to advertise the addresses for the H1, H2, H5 and H6. So you can check in this case, we need to configure IBGP, and IBGP is used like within a network, eBGP used between different networks, and so in this case we need to have the BGP peering from R1 with R2, R5 and R6, similarly from R2 with other 3 routers, from R5 with other 3 routers, from R6 with other 3 routers. Why with 3? Because if you are on R1, you need to have BGP session with R2, with R6 and R5. You can see here the color is blue. So all these are your IBGP speakers. These are similar to, like in our presentation example, we have P1 and P2. So you can relate R1 and R2 as a P1 and P2 in the presentation. So this is configuration for iBGP. I hope you are familiar with the BGP. If not, then I would again recommend you can go to APNIC Academy, do an online course with BGP, or find some other online courses we sometimes run on BGP as well. So let's go to R1 and we need to configure MPBGP. So how we do that? We go to the configuration mode, go to the routing option, autonomous system, we need to specify autonomous system for this router. Then we need to go to the added protocol hierarchy. We need to set RFC 8959 compliant. So you need to apply this in case you are implementing between 2 different vendors like Juniper and Cisco. If one router is from Juniper and another is Cisco, then you need to apply this command. Then you need to set the path selection router ID based on the external router ID, it can apply. You specify VPN apply export as well. And after that you can see here added protocol BGP group. This we are creating a group just to group all neighbors under all the neighbors under one group. So we do not have to give multiple commands again and again. So then we are specifying the family route target. Type is internal because this is IBGP, local AS number, local address, INET extended, unicast extended next hop we want to use for SRv6, and to advertise SRv6 service. Set family INET unicast advertise SRv6 service, accept as SRv6 service. So in normal MPBGP you just set family unicast, INET unicast. But here you have to write this advertise SRv6 service. So each node is able to advertise its SRv6 services. So let's configure it. Okay, commit and quit. Then remember we need to apply the policy to advertise the services. So that's why in the next step we are going to configure a policy. So we configure a policy. Here we are saying set policy option, policy statement SRv6 IBGP out. Like what if we want to attach a policy in outward direction for advertisement? We want to match a route, this route, and set the next hop as our SRv6 seed, and then accept it. And for the IPv6 address, we filter the we match the IPv6 address, set the next hop, and then accept. And for anything other, we do not actually accept, we just, that's the end of the policy. Okay, let's configure IBGP policy. Similarly, we can go to R2 and we configure IBGP and the policy as well. You can go to R5, configure the IBGP, configure the policy. Similar, go to R6, configure IBGP, configure the policy. So in case of policy is giving us the control to what we want to advertise and what we not want to advertise. How we will verify the routes? So this is giving you the explanation what you need to verify. So remember all the H1, H2, H3, H5 and 6, they have different IPv4 prefixes and IPv6 prefixes. So these prefixes need to be advertised. So once we have configured the IBGP, we need to check what is the like it's working or not working. So this is how we will verify. Show BGP summary. So you can see here so it's showing us the session and it's in the establish mode as well. So this is up down, up under the up down you can see 54 established. Similarly you can go let's go to R1 because this output is for R1. So if I click on R1, so you can see it is showing me a similar output which we have. So what are the different tables they are exchanging with each other, and the remote peer address and the state as well. So there is a description for this and explanation as well. Similarly, you can check the routing table, what you have received from the what you have in the routing table as well. So you can see 10.2.2.0/24 on R1. You can see 10.2.4. This is from R5 and from R6 as well. So you will see 3 different /24 if you give this command as well. Similar for IPv6, you should see 3 from other 3 neighbors. If you want to check from a specific neighbor, you can give command show route receive protocol BGP. This is the neighbor IP address for R2. So from R2, what I am receiving 10.2.2.0/24. So this is what this is representing. This is giving me this information. I am on R1. Okay, and I am receiving 10.2.2.0/24, and you can see it's been available on R1. That's mean from R2 I have received the information for this address on R1. Let's go back to the verification. So once you have verified this, then you can even match all of the different prefixes. So 1, 2, 3, 4. I have 4 hosts. 4 of their prefixes are available in the table. Similar for IPv6, you can confirm 1, 2, 3, 4. 4 host IPv6 addresses are there. So now I can go to H1 and I can test the connectivity towards H2. So in order to do that, I will open the command prompt here. You can see here the terminal. I will open this terminal and then execute ping command towards H2. From H1 towards H2. Let me. And you can see in this case it's working or not. So it's not working. It's showing me packet is getting lost. So why the packet is getting lost? There is some explanation here as well. Because when the packet is reaching to the end node, we have not defined the function what that needs to do. So we need to define the function, only then it can process it. So if I go to R1, so you execute this command, and you can see here the next hop here as well. So when the BGP is received from the neighbor, the next hop is this. But when the router is route is installed in the iNAT 0, the destination is, it's not showing same address. It's showing missing the colon 1. So we, in order to check this, we can even check on here. Do we have any flavors enabled? We have not defined any flavors. So we need to define this flavor UST. So once we configure the UST, then once the packet reaches to the device, it will be able to de-encapsulate and forward it. Okay, let's go to R1. We are already on R1. Let's enable the flavor UST here. So just see. So it's just enabling the flavor here. You can see here the command. So we already defined the end seed. We have already defined the behavior, but we need to enable the flavor. And in flavor, we are saying once you receive the packet, you are the ultimate end node. You need to de-encapsulate and then forward the packet. Okay, so we need to enable flavor UST. So let's go to R2 as well. So we just enable on R1. Let's go to R2 as well. And now go to H1 back. And from there, we will try to ping again from H1 to H2. And this time you can see I'm able to ping. But if I ping to H5, it's not working. On H6, it's not working. Why? Because on R5 and R6, we have not enabled the flavor UST. We have just enabled on the R1 and R2. So if I go to R5, and there I enable the this behavior, then it will start working again. So we have already the function defined, but within the function, we need to define what sort of behavior it needs to do with this function. Okay, so now I have defined the flavor on all of the nodes. So now if I check here, if I want to check on the router, once we have enabled this flavor, so see for the R1, R2, it's showing UST, but for R3 and R4, it's showing none because there is no service connected on R3 and R4. That's why I do not need to define any flavor there. I just need to, I'm defining the flavor where I have the customers. So you can see USD is just for R1, R2, R5 and R6. Similar, you have output here. It will help you when you will do the lab yourself. So after this, if you go back to R1 again, and even we can check connectivity just in one single command. So if I send this command, it will check the connectivity towards H2, H5 and H6 at the same time. So this is you can see it is showing me it has reached to H2, then it's H5 and H6 it will also show. So mtr command is also like a traceroute command, which actually gives you the information of the hop in between and also give you the packet loss information. Similar, you can check the connectivity on IPv6 addresses as well. So output has been given just to help you to match the same, that you are doing in the same or moving in the same direction or not. And again, you have some explanation here as well. Okay, so by completing this part, we have enabled the connectivity from H1 to H6, H5, and H2. So each one of them, they are able to talk with each other. So here we are just using the SRv6 and the BGP without the using any MPLS, without using any uh, like the VPN service or the VPN label. They are in the main routing table, but using the BGP we have like extended the reachability. In the next part, we have layer 3 VPN. So we have these two customer VPN site 1 and site 2. So our goal is to have have a connectivity from S1 to S2. So how we can like achieve this? What are the different things that we need to enable? So remember, we have already done some base configuration, like we have the IGP, ISIS, we have the MPBGP, and we just need to configure the VRF A on both sides, and then we need to uh, like advertise the routing information for the this VRF, and then they will be able to have the connectivity. So let's do it quickly. So where we need to do the configuration? So we have only two sites. The site is connected on only two routers, R1 and R5. The rest of the router we do not need to touch. So we will just go to the P routers, which is R1 and R5. These are our P routers, and they are providing the VRF. And in this case, VRF is R1, VRF1. This is the name of the VRF, and C devices R101, R201. Similar like we have C1 and C2 in the presentation. So where we also need to configure eBGP between R1 and C1 to have the routing information shared dynamically between the P and C router. And what we will do between the R1 and R5, we need to have the MPBGP, which we already enabled, but we will just add the VPN v4 and VPN c6 address family. The remote addresses, these are the peer loopback addresses, and the SRv6 end seed, this will be used at the update source when they are sharing the routing information. And this is the addressing detail and the VRF detail for the site 1. The AS number, VRF name, route distinguisher, route target, maybe you are aware with route distinguisher and target. They are actually used to keep the information of one VPN from another VPN. Like you have a VPN providing to a bank, now you want to provide a VPN to a maybe library or another bank. So their addresses should not be shared with each other or collide with each other. So you keep them separate using the route distinguisher, and you import the addresses from one PE to another PE using the route target. Okay, and this locator we are going to use is the main locator we have in this case, and this is the VPN prefixes we have. Okay, let's go to the configuration part. So we need to configure L3 VPN. In this case, we will go to R1. Okay, so I'm already on R1. So I need to configure the VRF or the VPN instance on the R1. So this is the configuration for a VPN instance on R1. Then I need to advertise the VPN routes within the, we need to update the IBGP policy to filter the route advertisement, because we already are not advertising everything. We are advertising specific route. So let me explain. So here you can see we have this term filter where we are specifying, okay, anything other than this we need to reject, because we are just advertising the prefixes from this. And then whatever is beyond other than this, we also need to reject. And after that we are saying any other thing, we need to set the local preference 201 and advertise it. So we are
set term 24 and set term
Sorry, the
comment,
term,
yeah,
this
term.
could be any number, but you need to put in sequence, because the first number will be executed first and then the second after that. Because when we are creating the term, we created 24 first. Remember in the previous step, if I go back, so here when we created the policy, okay, so let me see where we have. Term is 20. So the other term we are adding, that is 24 and 27 there. And SRv6 IBGP out. So the policy name should be same. So we are adding these terms here actually. So when you are setting these terms, so you need to set in the same order. Let me see if it's created accordingly, or show configuration, policy option, policy statement. So you can see first term 10, then term 20, then it added term 24, 26, then term 30. Because when you are adding new terms, they are automatically added at the end of. So previously we have 10 and 20, so new ones 24, they are just created below that. If you want to like reshuffle them, then you can even reshuffle. Then you have to specify insert term 24 before term 10, then it moves it above. Okay, so after that we need to configure the routing instance between P and CE. This is how we will configure the BGP from the PE router towards the customer router as well. And be careful on which router you are. This is R1. So we already done this configuration. Now we need to create the BGP from PE to CE. When I'm saying PE to CE, that's mean between these two routers. I need to create the BGP. Then after that, I will go back to R5 and do the configuration. I will go to R5 and do the configuration on R5, because we have two ends. Update the policy as well. Configure the R5 to R201 session. So that's mean this session we have just created. Okay, after that I need to configure the other side, because the customer side also needs to be configured. So I will go to the customer R101, and now I will configure the policy and then the BGP session. Okay, now you need to go to the other router, which is R201, and there also you need to configure the policy and the BGP session. So once you have done this, then you need to verify. So we have given some explanation there, the troubleshooting. Also there is a link. If you see this link with this icon, that's mean it is a URL. If you will click, it will open a new window just to give you help if you are not aware how to do the troubleshooting, or you want, because this sign is giving you the additional information. Okay, let's verify our BGP session. These are the different commands that you can use to verify BGP session. Show BGP summary. So again, you have two BGP session here with 172.28.0.2, and this is the IPv6 address. This is from R201 to PE to R5. Similarly, you can check the VPN table as well. This is relevant in case of R1 and R2, but for R201 and R2101, you can check these three commands. Okay, maybe there is a typo in command. Okay, so I think show route table. I think the BGP keyword would be additional. So here this keyword, I will correct this command show route BGP instead of show route BGP table inet. This is show route table inet 0. So you can see here we have the routing information. Like we are able to receive the routing information from the other site. And if I want to check the IPv6 routing table, I can use inet 6.0. And similarly, I can go back to like R1 and R2, which are the middle router, service provider router, or the carrier router. There I can check the BGP within their BGP table. Like I can see 172.24/13 and 24/30. So remember this, if I am on R1 and I am seeing this block, so you can see 172.24.0.0/13. So same I can see here. That means I am checking on R1 and this information is being advertised available here. So R2 has advertised it to R5 and R5 had advertised to R1. 172.24.0.0/13. So this is related to this site too and been advertised to R1. That's mean R101 will be also be able to receive this information. So let's go to the verification part. So once you have okay, let's go to R1 and from there you can ping the other side. Same for IPv6, you can try. So this is your point-to-point connection. That means this is between the R1 to R201. So we are just verifying this. We have like verified that BGP session is up when we earlier checked. And now we can also verify the point-to-point connectivity. I can check the routing instance, the VPN routing table. Within that, I have the BGP session up with the CE router. To check the layer 3 VPN routes, I can use these commands. Okay, and my information is matching what is available in the guide as well. That's mean I'm okay. And you can see here it's matching. So now how we want to be sure, like we have the connectivity from S1 to S2. So even we can check within the middle router as well. I can check the routes which are related to CR01. They have been received or not. And similarly, routes advertised from other sites. So what I am seeing here, since I am on R1, so even I can do an end-to-end check, or I can do check from the middle as well. So if you are having issue, then you need to check from the middle as well. If you do not have an issue, then you can just send up end-to-end ping. But if you are having issue, then you can do step by step, go to R201, then R1 and see from there. So like here, show routes received from P at P from CE. So this command is related to R5. So you can see here, depending on which router you are, like on R1, you will see the routes from 201, and on the, if you will go R5, you will check the route from R101. So these are the commands actually given just to help you in case you are having the missing any part or you are having the issue. So let's move on and go to CE, which is R101, and from there we can try to ping the connectivity towards the local address. Okay, now we can check also the BGP summary. Okay, we can check the routing table. It's showing me, so these are the local routes. These all 172.16, these are local, and 172.24, 26, 28, these are the remote. Because I am on, remember, I am on R101, and if I am seeing these routes, these are my local routes, and 172.24.0, these are the remote routes which I am receiving from the other side. So if I have these available, that's mean my routing table is complete. As a VPN customer, I am able to see the routes from the other side. So let's go back to the verification. So this means we are able to see the routes from other side. So we need to check the connectivity. And if you want to check what routes you are advertising from the customer side towards the other side, you can use this command. So it will show you what are the different routes you are advertising. So I think I'm on the wrong. I should be on the R201. Why it is not showing? Okay, so maybe the okay, so you can see actually need to provide the neighbor address, show route received at PE from CE. So that command will work on the R1 or R2 depending on which router you are. So if you check, give it the command here, then it will work. Okay, let's check the end-to-end connectivity. Verify this is for the P1. I will go to the last step where we need to verify the connectivity from S1 to S2. So let's go to the S1. Open the terminal there. And you can see I'm sending a ping request from S1 and it is going to S2. Similarly, if I want to check the path, I can use mtr command. So remember here, if you go up, what is the address? So you can see here the address for S2, it is 172.26.1.2. So the traffic is going from S1 to R101, R1, it is going to R3, then R5, then 201, and then reaching to S2.
So the ping test we are doing by the IP4.
We can do for IPv6 as well because we have enabled the both. Let me do for IPv6 as well. Okay, so here is my IPv6 address because we have enabled the connectivity for IPv4 and IPv6 both. So both address family on the VPN sites we are providing the connectivity. Within the middle we have only SRv6 which is IPv6 enabled. So this gives us the indication even we have in the middle IPv6, but on the edges we have IPv4 or IPv6 regardless of any service. we are able to carry that. And similarly, you can use MTR to see the path as well. It will not show, remember it's showing how many like gateway, 1, 2, 3, 4. So it is only showing the P router. It's not showing the R3 or R4 because they are not taking part in the VPN service. They are just the P routers. They are just acting as a transparent routers. So this is how you can enable the L3 VPN as well. The next is the traffic engineering, but due to the I think time, we will not be able to do that. But there are commands given and explanation is there. So here I can just quickly explain it. So remember, if our objective is instead of going this way, we want the service to grow from R5 to R6, R3, R4, R2, and then R1. So what we need to do, we need to create the list of segments that we want to go through. So first we want to create a path like this one. This configuration is related to the connectivity from R1 to R5. So what is our segment? First we will put the address of R2, then R4, R3, R6, and then R5. Similarly, in the configuration, we have created the SRT, segment routing traffic engineering tunnel here. So we will configure the SRT, and in this case, we put the address of 2, 4, 3, 6, 5. And then we have used this path.
We can use any number there, right? According to router, we
according to router you will use.
Okay.
Whatever you have configured with the router you can use, because what you have not configured, if you'll use it will be able to route it will just drop.
Okay.
So because we have enabled this, remember we have enabled this SRv6 SIDs on the devices. So that's why we are using these. And then once you have defined this segment list, so this is the name of the path we have created. Here you can see P1 to P5 via P2, P4, P3, P6. So we are using this as a primary path here. And then we are saying here, this is your destination address, the loopback address, and the color is 15. So this color is just the name number we are using. Okay, so once this, after this configuration, it will create the tunnel. Then we need to configure a policy to actually do the initial configuration to use this configuration to enable the segment routing traffic engineering. So in order to enable that, we need to do this additional configuration, go to the routing option, set route distinguisher ID, and set forwarding table SRv6 chain merger. This is like a command, actually mandatory in case of SRv6 Juniper, to enable the SIDS tags, because we are giving the list of SRv6, so it's help them to process that stack. Then we are saying set resolution preserve next stop hierarchy. So this is how in case of BGP it can know what is the next stop which need to send the address. Then we are saying set transport class auto create. So what the color we are creating, based on that it will automatically create a route based on that color. And then we are saying set protocol source routing use transport class. Whatever coloring or we have specified here, the color 15 for this tunnel, it will help to create that in the routing table. And after that we have a policy set policy option, and then member color 015. So this we are defining on the other side. Remember, we have created this tunnel from the R1 side towards R5. Now if we go to R5 and we set that color 15, whatever the traffic coming from here, so we say okay, use color 15 to send me traffic for what is traffic for R201. So then it will be able to map that traffic using this color over that. Remember, if we need to go from here, like outside on a 2 destination, and we have defined, okay, color 5 is for Tokyo, color 15 or blue is for Tokyo, color red is for Kyoto. So whomever I will give the 15 or blue color, he will know I'm going to this path. And whoever is given the other color, he will go to other part. Similarly, router automatically map the customer traffic using the color over a certain path. So once you enable this configuration, or you complete this configuration, so you are able to force the traffic. And I have given some explanation here as well, how you can verify. Like you can see here we have not enabled the SRT, traffic engineering, and segment list is equal to 0. But once you have enabled this configuration, so you will know that the segment list will appear here. So this is how router knows, like, now I have to go through this segment to reach to the destination, and without that it does not know. It just know, like, okay, there is one segment which is like the destination segment. It don't care what is the path in the middle. And once you have configured this again, you can verify the configuration and send the end-to-end ping request to check your connectivity. So I hope you will you have spent like 2 sessions, you have learned something. And if you have any questions, you can ask me now, or you can have my email address. If you go to APNIC Academy, click on upcoming events. So you have my email here, you can send me an email as well. Otherwise, the slides are available here. The lab link is available here. There are some additional references which you can go through at your own time if you need to like study more in this case. If you have any question, you can still ask me now. Do we have anyone on the Zoom, or was there someone on the Zoom session? So I would request if you can complete this survey as well. There is a link for the survey. If you go to the course material page, click on the quick links, there is a participant survey.